All right, let me get the chat window open quickly. No, the due dates on Gradescope are not correct. So I had to, but I don't know what the due dates are for those things because I don't know what pace we're going to cover things at, or we might not quite finish what I think we should finish. So I can't set a correct due date, but I wanted to have everything up there anyways. So at the end of each class, once I assign the correct section, then I update the due dates on Gradescope. So yeah, so only the most recent ones, the ones that are due have the correct due dates. The ones that I haven't yet assigned just have the last day of class as a due date because I had to put something. So any other questions while we're getting started? No, 16, that's good today. Oh, someone had a question. Philip, were you gonna say something?
I was just gonna say, I thought the ones that were due today had the wrong due date.
Oh, did they?
Yeah,
Oops.
I think
Okay.
every single one of them said in 2 weeks.
The ones due today said they were due in 2 weeks from now?
Yes, I believe so.
Oh, okay. Oops. I didn't mean that happened. I made a mistake. I'll go and fix it after class.
And then I also had one more question, if you don't mind.
Sure, no problem.
When we're using the fundamental theorem of line integrals,
Mhm.
do you care if we parameterize a whole function in terms of t, or if we just plug in a x, y, z coordinate into our function?
If you use the fundamental theorem of line integrals, and so when you say plug in the x, y, z coordinate into the function, you mean
For the
the
bounds?
potential function and not
Into
the
the
function. Yeah, no, that's fine. You don't have to parameterize at all. The benefit of the fundamental theorem of line integrals is that you don't care what the path is, and so you don't have to parameterize at all. You can just evaluate at the endpoints.
Okay, that's what I thought.
Sure.
Thanks.
Good. Any other questions? No? Okay, guess what's coming up? On Tuesday, it's gonna be a little exam called Exam 3, and you're all ready for it, except for Green's theorem, which we're about to talk about. And I just wanted to remind you of something. I said it last time. We're gonna be careful to do it on every problem. And this is also gonna be true for the homework. It's also gonna be true for the exams. So I said homework problem, but really for any problem, it doesn't have to just be homework problem. Any problem that involves a theorem, here are the components it has to have. It doesn't necessarily have to be in this order, although I think maybe some students might like it if I like have a step-by-step thing. So I'll try to do it as a step-by-step thing, but it doesn't have to be in this order. But these components have to be there. If you're going to use a theorem, you have to tell me what theorem it is you're using. Otherwise, how do I know what you're doing? And some of you will say, and rightly so, one of those theorems didn't even have a name. They're totally true. But that one isn't one that you use in a computation. So it's okay. The ones you use in computation, you have to name them. And then you need to both make it clear that you know what the hypotheses are, and also make it clear that the current problem you're on satisfies those hypotheses. You can do those both together or however you do it, but I need to know that you knew what it took to use this theorem and you checked that you had the right conditions. Okay, so that's 2 and 3. And then whenever you're doing a computation, you need to show me where it is in the computation you've used the theorem. So I did that last time. We'll keep doing it. You'll get used to it. I just want to be sure I've called it out a couple of times. It'll also be on the instructions for the exam. So yeah, so just make sure everybody knows that. Any questions about that? Nope. Okay, I just heard back from the grader. The other class doesn't know yet because I saw it in between. And he promised to have the grading for all the homework done by Saturday evening. So you'll have Sunday and Monday to look at the returned homework. I hope he can do better. Apparently, I guess his mom is recovering, so that's good news. And we'll see. But he said definitely by Saturday evening, so you'll have a couple of days to look at your homework and ask questions and so on. Okay. All right. So the last section before the exam is Green's theorem, and as I said before, I'm going to tell you about Green's theorem and how to use it. But the meaning of why it's true, Green's theorem is so cool. Already it's cool enough if you don't know why it's true, but you can still use it. It just saves you a lot of hassle in certain circumstances. But whenever you find out, whenever you understand it and understand why it's true, it just like it feels good to, it feels, I don't know, comforting to know that the stuff that you're just replacing has some meaning. But we won't really be able to understand the meaning until after we do 13.5, so that'll be after the exam. But right now we can do 13.4, part of it, and that's green theorem. And in order to talk about Green's theorem, I need to give you a couple of more pieces of terminology, that sort of thing. So let's just go back to, let's talk about orientation. So if we're in the case that we have a simple closed curve. So for this thing, let's suppose C is a simple closed curve. What do I mean by simple?
It doesn't have any intercepts?
Yeah, it doesn't have any self-intersections. Good. And then closed, what does that mean?
Same endpoints.
Yeah, same endpoints. Okay, so simple and closed, those go together. The reason we put those together so much is because if you have a simple closed curve, so let's think about this one, for example. You have this really nice feature that there's an inside and an outside. That's not true when you have a curve that's not closed. And when it's simple, then it's kind of confusing because there's this sort of swap over. And I mean, if it's not simple, you can still do stuff, but it's too complicated. So if it's simple and closed, then you have an inside. You have it cuts off a region. So if this is my curve C, there's a region inside of it. And that's why simple closed curve matters to us. And so C is a simple closed curve. And remind me, what does it mean to have an orientation?
Just like an arrow on the line that you go around it in.
Yeah, it's a direction. It's like an arrow on the curve of which direction to go around it. So there could be, each curve has two possible orientations. One would go, that way, and then the other one would go the opposite way. Those are two different orientations. So an orientation is just a choice of direction to head along the curve. Okay, so you can't always do this. Usually you can't. But in the case when you have a simple closed curve, then we can do the following. We can have a favorite orientation, a preferred orientation. We call that the positive orientation. So here's the definition. In this particular case, the positive orientation for C is the orientation that, it's going to take a lot of words. It's the orientation that if you walk along the curve in the direction of that orientation, the region that's being cut off is on your left. So here's the region. Let me write the words down. Positive orientation for C is the orientation such that, so is the orientation where if you walk along the curve in the direction of the orientation, the region is on your left. Okay, so looking at this curve and the two orientations, there's the blue orientation and the orange orientation. Which one of those orientations is the positive orientation?
Orange.
Orange, yeah, good. So this one is the positive orientation. Okay, so you may be tempted to say, why are we saying all this stuff? I'm just going to say counterclockwise. So let me just say, not necessarily counterclockwise. See, one thing about mathematicians is we are efficient and we are precise. And so if we do something like write some huge long definition about moving in the direction of the orientation, regions being on the left, blah, 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 if we could have just said counterclockwise, we would have just said counterclockwise, okay? So the reason that, that we give this big long definition instead is sometimes, so curves, I haven't given an example of this yet, but a curve might not be connected. So it might contain two pieces or more than two pieces. So think about this situation where we've got this curve made up of these two components, and I'm talking about the region that's in between them. So this curve C is made up of two components, component 1 and also component 2 union together. And so let's say here's component 1 is going to be on the outside, component 2 will be this inside curve. If I want to put an orientation on the outside curve, I want to cruise in the direction that the region's on my left, and sure, in that case, it's counterclockwise. But let's think about C2. If I head around C2 in the counterclockwise direction, I don't have the region on my left anymore. I have to go C2 in this direction. So it depends on where it is. Also, this definition of positive orientation, this is going to carry over to when we're in 3 dimensions. And in 3 dimensions, counterclockwise doesn't mean a single thing. So we really need this cumbersome definition to describe. So let me just say, this is positively oriented with the yellow. Okay, positive orientation. Let me give you a little bit of notation. Well, does anyone have questions? Can I re-explain anything that got confusing? Okay, here's a little bit of notation. Okay, one piece of notation is if D is the region inside your simple closed curve C, then this notation looks like partial derivative of D. It's the same symbol, but we call it the boundary of D. So that symbol means the boundary of D. So C, but with a positive orientation. Okay, so that means, you know, if this thing right here is the region is D, then the boundary of D is made up of both of these curves together with their positive orientations. And you might have a side complaint, and I wouldn't blame you if your side complaint was, why use this symbol? I mean, you might think we're just trying to confuse you because you're used to that symbol meaning take a derivative, and you can't take the derivative of a set of points. And why not use literally any other symbol but a symbol that already has a meaning? But actually, there's a good reason. And this is just a side comment. This isn't really something that I'm going to test you on or anything, but I want you to understand where this comes from. So let's just think about boundaries and relationships. Like, we're going to think about shapes and their boundaries and the relationships between the sizes. Okay, and so like a size in 2 dimensions means area, and a size in 1 dimension means length, and a size in 3 dimensions means volume. Okay. So if I have a circle and I think about the disk inside of it, let's say the radius is r, the area of the disk, let's say the disk is called d. Well, okay, the area of the disk is, we know what that is, it's pi r squared. But the size of the boundary of the disk, which would be length, is 2 pi r. 2 pi times radius is the circumference. Look at the relationship between those. The size of the boundary is the derivative of the size of the original thing. Okay? That's not a coincidence. If you also think about, like, let's say you have a sphere, which is the boundary of a ball. The volume of a ball is 4/3 pi r cubed. And if I consider the boundary of it, that's going to be a sphere, and the surface area of the sphere, the boundary of the ball, is 4 pi r squared, the derivative. Okay, so so it makes sense to see that connection and use this symbol for boundary. All right, so that's one piece of notation, and then the other piece of notation is this symbol. So the symbol. If I'm going to do the integral over some curve f dr, but I add this piece to it, a little circle around the middle of the integral symbol, then that's referring to, that's saying a lot of specific things, that we're doing a line integral, obviously, but around the curve C, obviously, but C is a simple closed curve with a positive orientation. So there's a lot of information there. So this is the line integral around C, but C is a simple closed curve with a positive orientation. We use this so much, simple closed curve with positive orientation, simple closed curve with positive orientation, that we have the shorthand notation just to put all that together. So that's what's being said when we do that. Okay. So all that's just a warm up so I can tell you what Green's theorem is. Are there any questions right here before I get to it? Let's talk about Green's theorem. Like any quality theorem, it's got some hypotheses. Let me tell you what the hypotheses are. So you need to suppose, first of all, C is a positively oriented simple closed curve, just like we've had above. C is a positively oriented simple closed curve in the plane. That means Green's theorem only works in 2D. There's another theorem called Stokes' theorem that works in 3D, which we'll talk about later on, but Green's theorem only works in 2D. Okay, so C is a positively oriented simple closed curve in the plane. And then D is the region inside. Remember, anytime you have a curve, there's going to be a region that it bounds. So we're just going to give that a name. D is the region bounded by C. And well, there's another condition. You also need P and Q. These are going to be functions. They have to have continuous partial derivatives. Okay, if you have these three conditions, then here's something that's true. Then if you wanted to do the line integral, the positively oriented line integral around C, which, by the way, is the boundary of D. Here's standard, remember this is the alternate notation for a line integral of P dx plus Q dy. If you want to do that line integral, You could do that, or you could replace it with this double integral. It's going to give you the same value as the double integral over the entire region of dq dx minus dp dy dA. Initially, you might, okay, so why would you ever use this? One good thing about having a theorem like this is if you're trying to do this, if you're trying to do this and it's too hard, maybe you can do this. If you're trying to do this and it's too hard, maybe you can do this. So you can swap back and forth. The same way, you know, changing the order of integration was good to know because you could go back and forth. Or same way, converting to different coordinates, more appropriate coordinates, is good to know because it makes your computation easier. It's good to know this because sometimes you can swap it for a computation you can do. You might look at this and say, why would I ever do this? Because this is a one variable integral and this is a double integral. Isn't this twice as hard? In fact, no. Usually this is harder, to be honest. Why is this harder? Well, what does it take to do a line integral of a vector field? First thing, parameterize. Second thing, check the orientation. Third thing, turn everything in terms of t, and then move on with your life. Sometimes these formulas are complicated. Also, sometimes these partial derivatives are super simple. And so, anyways, that's reasons to use it. So there's the theorem, and I'm going to do one example where we verify Green's theorem. Not the same as proving. Can anybody tell me what the difference is between verifying a theorem and proving a theorem? What do you think?
Is verifying like trying it with one case and then proving it is for all cases?
Yeah, that's right. Thanks, Sarah. So verify means I'm just going to do one example and see, hey, it worked in that one example. But proving it, I'd have to prove that it works for every possible example, and that's not what we're going to do. So the reason that I'm doing this one example isn't really because I think you don't believe Green's theorem, because I'm sure you do believe it. And just because, you know, it's got a name, it's been in textbooks for a long time, whatever. And doing one example certainly doesn't prove it. But the reason I'm doing it is because you may look at all these symbols and be like, oh my God, I don't even know what any of this is. So if I do the left-hand side and I do the right-hand side, you'd be like, okay, now I kind of see what's being talked about here. So that's what I'm going to do right now. I'm going to verify Green's theorem for this special function. So here's an example. Verify Green's theorem for the vector field f of xy equals x plus y, where am I, comma y, over the unit disk. Over the unit. I wish I'd said circle, but whatever. This is, either one's fine. Verify means I'm going to have to evaluate the left-hand side. And then I'm also going to have to evaluate the right-hand side. And then I'm going to hope that I got the same answer. So that's the idea. Okay, so let's just do them both. Let's do the left-hand side first. LHS for left-hand side. So I really want to evaluate the line integral around the boundary of the disk, PDX plus QDY. Unit disk, here's the boundary of the disk, positively oriented. What's the very first thing I have to do?
Parameterize.
Parameterize, that's right, always. We have a line integral, first thing you have to do is parameterize. So we're parameterizing the boundary of the disk. We know how to do that. It's the unit disk. The boundary, that's the unit circle. And so the parameterization is just like we always do a circle, cosine t, sine t, t between 0 and 2 pi. What's the next thing?
Check if it's orientation preserving.
Check if it's orientation preserving. Excellent. So we don't want to forget that part. So let's check the orientation. Well, let's see. The problem asked for, since it was asking for Green's theorem, to verify Green's theorem requires positive orientation. And I even put that right here, right here. So the problem asks for a positive orientation. And in this example, a positive orientation is counterclockwise. We're going to say counterclockwise a lot, so we can write CCW if you want for counterclockwise. Okay. Our parameterization, cosine t, sine t, starts here and goes counterclockwise as well. So it's an agreement. Our parameterization is also counterclockwise. So orientation preserving. Okay, now I just have to go and evaluate the line integral. Remember, the convention is the first component function is called P, and the second component function is called Q. And when I'm parameterizing, this is the X component, and this is the Y component. And everybody, this is a line integral. Everybody has to be in terms of that one parameter, which is T. So when we evaluate this, evaluate the integral, I've got the line integral, positively oriented line integral around the boundary of D of P dx plus Q dy is, okay, everybody's in terms of T. T goes from 0 to 2 pi. Now I want P. P is X plus Y, but that has to be in terms of T. Maybe I'll put this intermediate. The last class was kind of confused. It's weird for me to have these mixed variables. Normally you wouldn't do that, but since the last class kind of got confused, maybe I will. This would be X plus Y. And then the dx, if I look, here's X. So dx, if X is cosine T, then dx is negative sine T. Plus Q is just plain old Y. And then dy, derivative of Y is cosine T. Everybody's dt. So do y'all see where all those pieces came from? Let me just make sure. This was the P, and this was the dx, and this was the Q, and this was the dy. Okay. But this is no good because I can't have 3 variables in there. Everybody has to be in terms of T. And remember, we only care if we're going to do the line integral around the boundary. We only care about the values of the vector field on the curve. We don't care everywhere else. So what gives us points on the curve? It's the parameterization. This is what we plug in when we see X and Y. So here, this is going to be integral 0 to 2 pi. Can't fit that there. X plus Y is cosine T plus sine T times negative sine T. And then Y is just plain old sine T times cosine T dt. Okay, let's multiply out. So I have negative cosine T sine T minus sine squared T plus sine T cosine T. Oh, cool, that cancels. So I have just a negative sine squared T. Luckily, we're getting good at trig integrals now, so we remember this is just, we use the half angle formula, right? So this is minus a half, 1 minus cosine 2t. So antiderivative of 1 is t, and this is 1/2 sine 2t from 0 to 2 pi. If I plug in 2 pi, I'm going to get 2 pi minus a half sine of 4 pi plus 0 minus a half of 0, sine of 0. That's 0, that's 0, that's 0. So I'm just going to have negative pi. I know I charged through the computation, but normally I just want to skip a lot of the integration because that's something that you can sort of do in the privacy of your own home. The important part is I want to be sure you understand where all these bits came from, so you know how to set it up. So any questions on this left-hand side integral? All right, let's try the right-hand side. So going back to Green's theorem, so we did the left-hand side, which is this thing. Now we need to do the right-hand side, which is this part. Double integral dq dx minus dp dy. So now evaluate the right-hand side. Double integral over all of d dq dx minus dp dy. Okay, I have the same region. There's our region D. So let's see. So this double integral is dq dx. Let's go back and remind, well, let me just remind us, where can I put that? I'll move this down a little bit. Okay, let's remind ourselves of what P and Q are. P was x plus y, and Q was just y. That came from the original function right here that we were trying to integrate. Okay, I'm just, since we can't see it all on the screen, I'm just rewriting it. Okay, so let's see, dq dx. Q is just y. That's a constant, so partial derivative with respect to x, that's just 0. dp dy, that's 1. Look how easy that is to integrate. Actually, you don't even really have to integrate it because this is negative. And this thing right here is the area of a disk. So we could just say that's a negative pi already and be done with it. But if you didn't spot that, you might be like, oh, what if I didn't see that? That's okay. It's easy enough to do this computation. What's a good choice of coordinates to use? What do you want to use?
Polar.
Yeah, it has to be polar, sure. So if we use polar coordinates, well, the dA becomes an r, dr d theta, and r goes from 0 to 1, and theta goes from 0 to 2 pi, and we just integrate. So that's going to be 1/2 r squared and that's going to be 1/2 of 1 squared minus 1/2 of 0 squared. Then if I integrate that with respect to theta, I'm going to get 1/2 theta from 0 to 2 pi, which is negative 1/2 of 2 pi plus 1/2 of 0, so negative pi, just like the other one. Okay, so the left-hand side equals the right-hand side, and so we verified Green's theorem. in this case. Okay, so that's what both of the sides look like. And if you think about it, this one was a lot easier to do than this one. This one required parameterizing, checking orientation, plugging all the stuff in, and so on. Okay. Sometimes, oftentimes, it'll be true that that the double integral side will turn out to be easier. Not every time, but sometimes. Okay, I'm going to do another full example, but I want to just see if there's any questions about this first. Give me a minute to ask. Anything I can say more clearly? Okay, let's try another example. How about, so this example is, oh, wait, I have a question for you. I didn't check any conditions. Did I make a mistake? Am I going to lose points for that? Oops, sorry. What do you think? Be good to know the answer to this because you're about to have a chance to lose points.
0 points because you didn't say where you used the theorem.
Ha, it could be 0 points because I didn't say where you used the theorem. Actually, I don't need to check the conditions in this case or say where you use the theorem, although usually I do. But in this case, I didn't actually use the theorem. All I did was, in this side, I calculated the left-hand side directly without using any theorems at all. And on this side, I calculated the right-hand side directly without using any theorems at all. So this particular example that I did, verifying Green's theorem, I didn't use Green's theorem. I just showed that both sides were equal with a direct calculation. So here, I didn't need to check any conditions, but I will for the next one. Otherwise, you're right, 0 points for not saying whatever. Okay, so let's try, probably not 0 points, but you do some points. So let's try this example. Let's C be the boundary of the rectangle. One, 3 cross 2, 3. What is this line integral? Line integral, positively oriented around C of 2y squared plus x to the 5th dx plus 3y to the 6th dy. Okay, so you may be confused about this notation. We've had it in a couple of problems, but just in case you're confused, let's think about it. So just like for the this is a Cartesian product of two sets, and the two sets are intervals. One interval is between 1 and 3, and the other interval is between 2 and 3. And Cartesian product is just like if I have r cross r, or I write it as r squared, that means I've got two coordinates, and the first coordinate comes out of the first set, and the second coordinate comes out of the second set. So they're ordered pairs where the x value comes out of there and the y value comes out of there. That's the idea. So if I want to graph this rectangle, the x values can be between 1 and 3, and the y values can be between 2 and 3. So I've got this. This is the rectangle. Let's call it D for the region inside. C is the boundary of that rectangle. So, so C is actually, let's do another color, I guess. C is actually this thing right here. If I were to do this, oh, and it's positively oriented. We're asking for the positively oriented thing. So here's positively oriented like this. If I were to do this problem directly, how many parameterizations would I need? 4. Sarah held up her fingers. 4, right? Because I need to, because if I parameterize this line segment right here, that's going to have a totally different formula than this line segment. Different formula, different formula. I have to do 4 different parameterizations and then check 4 orientations and then do 4 separate line integrals and then add up all the value and be done with it. Okay, so so I hope you can see that that's will be a pain in everybody's butt. But don't worry, Green's theorem to the rescue. So we're going to use Green's theorem and we're going to announce this to the world. So we want to use Green's theorem. And in order to do this, we're going to make sure we have the conditions. So let's go back and look at the conditions. Here they are. The conditions say this, make it green. So I can't help, I have to tell you. Green's family is still around in England somewhere, in Nottingham, I think. And they have a windmill. And a friend of mine actually went and visited the windmill, and they sell little pencils that have Green's theorem written on the side of it in green, and he bought me one, so I have one of those. So if you stop by next year and see me, you can come, you can visit the Green's theorem pencil. You're gonna love Green's theorem so much that you're gonna wanna visit the pencil. Okay, so here's Green's theorem, here's the conditions. Positively oriented simple closed curve, D is the region bounded by C, continuous partial derivatives. Okay, let's try to do these things. Okay, so here's what we need. I don't care if you list them off first and then you tell me which ones you have, or if you put it all together. However, we just have to have the name, the conditions, showing we have the conditions, and then where did we use it. So we need, first of all, simple, positively oriented simple closed curve. And we look at our C. C is the boundary of a rectangle, so C is closed. And the question is asking, right here, the question's asking for a positive orientation, so we've got that. So C is the boundary of a rectangle. So closed. And the problem's asking for positive orientation. Okay, fine, that's totally enough to just announce it. 2, I need D to be the region inside of C. Well, that's not really a requirement as much as it is so you know how this thing is connected to this thing. It's just a labeling of things. So if I didn't have a D in the problem, which, the problem didn't give me a D. If I look at this problem, there's just a C in it. So I'm just going to say, let D be the region inside of C. That's fine. And then the last thing has to do with partial derivatives. Well, let's look at P and Q. P is 2y squared plus x to the 5th. Q is 3y to the 6th. What are those partial derivatives going to be like? They're all polynomials. I can write them down if I want, but if I look at them, they're all polynomials, right? So if I take the partial derivatives, I just get polynomials. All partial derivatives are polynomials. So are continuous. You don't have to make a huge deal out of it. I just want to know that you knew what you needed and you checked it out. Okay, so here, we knew what we needed, we checked it out. Now we have all the conditions to use Green's theorem. So let's use Green's theorem. So here's what we do. Do not start with the other side of Green's theorem for 2 reasons. First of all, you won't be able to show me where you use Green's theorem. That would be bad. But second of all, you're not really answering the problem. If I said to you, hey, what's this line integral? And you said, the double integral is this, I'd be like, you're insane. I asked you for a line integral, right? So you start with a line integral, and then you apply a theorem to what they've asked you for. So if we start with what they asked you for, they asked us for the line integral around C of 2y squared plus x dx plus 3y to the 6th dy. But I want to apply Green's theorem, so I'm going to, if I apply Green's theorem, that means I'm going to exchange it for the double integral over d of dq dx minus dp dy. And right here, this is where I used Green's theorem, so that's what I'm going to say, by Green's theorem. And then do the rest of the computation. So let's see. dq dx, remember this one is q, and this one is p. Partial derivative of q with respect to x. Hey, there's no x's there, that's just a 0. dp dy, that's 4y. dA, here's the region. Rectangular coordinates are obviously a good choice for a rectangle. So dx dy, let's say. So x goes 1 to 3, y goes 2 to 3. This is a much simpler integral than doing 4 little sub-intervals, integrals of this sort of thing. Okay, so let's just do it because we can. So negative 4y with respect to x is negative 4xy from 1 to 3. So plugging in 3, I'm going to get negative 4 times 3, so negative 12. What does it keep doing there? Negative 12y, and then plus 4y. Did I do that right? Negative 12y plus 4y, so that's negative 8y from 2 to 3. Then if I do the antiderivative of that, I'm going to get negative 4y squared. So negative 4 times 3 squared, negative 4 times 9, negative 36. And then plus 4 times 4 is plus 16. So that's going to be negative 20. Okay, I know you can do all those bits. I just wanted to show you really this part right here. We replace this integral with this integral, and hey, that was easy to do. Is there anything you want to ask about these?
Is there a reason we have to replace it with like the dq and the dp symbol? Is there any other notation? Like, cause like it doesn't say dp in the original. So do you have to like label what's dp and label what's like label what's
I
p
see.
and what's q?
Because the original, yeah, you're right. It's probably nicer if I said, as part of this write-up, it's probably nicer if I said, let p be 2y squared plus x to the 5th, oops, x to the 5th, and q be 3y to the 6th. Yeah.
So there's
Whatever,
always p
whatever
is the dx and q is the dy.
Yes, that's right. That's always going to be true.
On the test, is it gonna like explicitly say which theorems to use, or are there like key things we should look for? Like, I don't know, now I feel like there's just a lot of theorems and I'm like,
Oh.
I don't know if I'll be like sure when to use.
That's the $1 million question right there. So I was going to give, and we have time, I'm going to give you a short problem to work on yourselves to make sure you feel confident about this. But then the next thing I was going to do was show you the fun pack. So so you're absolutely right that each of these techniques, whether they're hard or not hard, it doesn't tell the whole story. The whole story is there's a whole lot of theorems, and how do you know which one to use under what circumstances and so on? Well, one answer to that is if you don't have the hypotheses, then you can't use the theorem. And another answer to that is play with the fun pack, because see, I made the fun pack on purpose because it has all these problems, but you don't know what to use on it, just like the same situation will be on the test. So it'll help you get stronger with that sort of thing. So after we do this one practice problem together, then we'll go look at the fun pack and we'll just talk for a few minutes about what's a good approach for some of the problems and try to build up that kind of intuition a little bit. But you're going to get better and better at it just by doing more problems. Okay. And you're absolutely right. That's a huge challenge. And that's what doing the fun pack is going to help you with. Any other questions? Okay, let me give you a classwork to work on. We're not going to take that much time on this, so I'm not going to do breakout rooms this time. But if you have questions, you can ask, or you can type in the chat or whatever. Let's just have this classwork evaluate. So this line integral, positively oriented curve C, 3y minus e to the sine x dx plus 7x plus the root of y to the 4th plus 1 dy, where C is the circle, x squared plus y squared equals 9. Take a couple minutes on that and see what you can do with it. And like maybe 5 minutes, and then I'll come with you. And I'm just gonna mess around the house. If you have questions, say something and I'll hear you. So 4:58, I'll be Okay, let's talk about this problem together. So you probably have a lot of this already. So we know we're going to use Green's theorem. And what do we need? We need a positively oriented simple closed curve. And we have that. C is a circle, so it's a simple closed curve. The problem asks for positive orientation. I just sort of remarked that. I've got that condition. That's the biggest condition, really. So I need to be sure to lay that down. D, whatever, I can just name D the region inside C, that's fine. This part about the partial derivatives, I thought we'd take a second to talk about. So if I think about the partials, so Px is just minus e to the sine x times cosine of x. Py is 3, qx is 7, qy is 1/2 y to the 4th plus 1 to the minus 1/2 times 3y, times 4y cubed, sorry. Okay, so if I look at that, first of all, I realize I didn't give myself enough space, but if I look at that, are all of these continuous? Are they obviously continuous? This one is. Sine and cosine are continuous everywhere. E to something continuous everywhere. This is the composition of continuous functions. This is no problem. 3 and 7, no problem. What about this one? Could there be a problem or no?
You have y to the 4th, so I think, wait, you can't have a negative in there, so I think you're fine.
Yeah, that's right. See, there is a denominator in this, right? The denominator is square root of y to the 4th plus 1. So then you have to worry, is that going to be 0? But then Philip just convinced us. See, y to the 4th, that's always going to be positive or 0. And if I add 1, it's always going to be positive. So I'm never going to have a 0 in the denominator. So I'm just going to say something quickly about that. Px, Py, Qx, all obviously continuous. And Q sub y has a denominator of the square root of y to the 4th plus 1, but that's never 0. Okay, I need to move all this down because I didn't leave myself enough space, so be patient with me for a second. Okay, what I wish I had done here is announced the point of this section. Oh, oops. So this is region. We need to see that all partials continuous. And they are, because we looked at them and we don't have a problem. Did anyone have a question about that part? That part may have been a part that you were uncomfortable about. You don't have to say that much. I don't really need a full analysis of each of the functions. I need to know that you've thought about what you have and you recognize that there's no problem with it. So say something so that I'm clear that you thought about it. And then here we are, we're trying to do this line integral, but we're like, no, thank you. I don't want to do the line integral. I'd rather do this double integral. And since I did that, this is where I applied Green's theorem. So I say by Green's theorem. Between this line and this line, this was fine, but when as soon as I said it was equal to this, that's when I applied the theorem. And then I just applied the theorem, and look, whatever, it's 4 times the area of the circle. You could have set it up as a double integral, you still would have got 36 pi. What do you want to ask about that? What should I clarify? Are we good on that? Okay, then that's all I want to say about Green's theorem. There's some Green's theorem homework. There's some homework posted for 13.4. You don't have to turn it in. You're going to want to do it because you're going to want to practice, okay? But you don't have to turn it in ever. But what you the other thing you're going to want to do is this fun pack. So let me try to find, where is this thing? Oh my gosh, where did you go? There it is. Okay, this fun pack. So let me new share here. Great. Okay, you have it. It went to the wrong thing here. So here's the fun pack. This is on your website. You can access it just fine. But I wanted to call our attention to it a little bit, just so we can talk about the issues that Yasmin brought up. The best thing about this fun pack isn't just that there's clearly hours of fun to be had, but the best thing about this fun pack is you don't know what the best technique to use is. And so this is your practice for getting good at that. So notice that I said it here. Let me do this, annotate. Okay. Notice that that I said here. Can you see the mouse? Okay. Notice that I said here, assume counterclockwise orientation on all curves, unless you're said otherwise. So in case you don't see it down here, I just want to point out that that's going to be for these problems. Okay. And use a theorem when you can. Go directly when you can't. Let's look at this first one. And try to think. So what theorems do we have even that will help us simplify integrals? What theorems do we have? I'll try. Green's theorem. We just did that. What's another one?
Theorem 6.
Theorem 6. Ah, well, theorem 6, we do have it, but theorem 6 will determine whether a vector field's conservative. How can that help us evaluate a line integral?
Use the fundamental theorem of line integrals.
Oh, yes. Use the fundamental theorem of line integrals. Okay, so those are the two theorems. Oh, by the way, I guess it does say right here, these are the two theorems you want to use. Okay, so use those things if you can. So let's look at this problem. Can I use Green's theorem on this problem? Number one. When I'm asking that, what I'm really asking are, do I have the conditions? Have I satisfied the hypotheses? What are the conditions?
Counterclockwise, but this one's a clockwise, so we can't.
Ah, okay. I'm glad you brought that up. So it does say clockwise, and that wouldn't be the positive orientation. That could be a problem. I should have mentioned this. And it's too late for me to scroll back, but what if the curve wasn't positively oriented? Here's what we could do. We know that the integral around the negative orientation has the opposite sign of the integral around the positive orientation. So we could say, the integral around it oriented this way is the negative of the positive orientation, and then we could use Green's theorem from there. So you're right that there's some more dealing with that you have to do, and doesn't obviously fit, but we could still work Green's theorem in to that situation. But there's a different reason that we can't use Green's theorem. What else do we need?
So the partial derivative would be discontinuity, would have some discontinuity.
Discontinuities, that's a big thing. But let's see, where's the discontinuity? At the origin. And this circle may or may not contain the origin. So it's possible that this could still be okay. Even though you're right, it does have discontinuity somewhere, it might not have discontinuity on the region. We'd have to investigate that a little bit more, but you're right, that might be a problem too. And there's another problem. In fact, all three of the conditions might be violated. What's the other condition? We have to have a closed curve. And what do we have? Dear God, I'm going to try to draw with my finger on this. So just we have some circle. The center's at 6, 3, right? So the center's way over here somehow. And it's not doing a dot. Okay, center's something here, then I've got this circle, it's a radius 7, so yeah, I can't do a circle with my finger, whatever. It's like this, but I don't have the whole circle. I only have it from 13.3 to, this is how to get to -1.3. So I really only have, I don't have this. I really only have, let's see, with clockwise orientation, I only have, oh, oops, oh gosh. Sorry, this is horrible. Clockwise orientation, I only have, I guess it would be this way or something. The point is, I don't have a closed curve. Without a closed curve, I'm lost. I can't fake the orientation. I can't hope that the discontinuity is away from the center. There is no middle. There's nothing I can integrate over. And sometimes students will make a mistake and they'll see, here's an axis. They'll say, oh, look, this is a region. I'm going to integrate over this region. No, this axis just happens to be a line there, but that's not part of the problem. That's not bounding anything. Okay, so be careful about that. I apologize about the horrible drawing, but I hope you get the point that there's no, it's not a closed curve, so there's no way we can use greens. Not possible. Okay, so then what about fundamental theorem of line integrals? What do we need for that?
We more or less need to be able to integrate it, or you need to find what needs to be conservative.
Yeah, it needs to be
Technical way.
conservative. Absolutely. That's a huge condition. It needs to be conservative. And so you're right. We'll need, like, in order to go forward, it would have to be conservative and we would have to be able to find a potential function. So if I look at this, I'm just going to try to eyeball it right now. Does it seem like both of those could have come from the derivative of the same, you know, the x partial and the y partial derivative or the same function? That looks likely to me because they both have the same denominator. One has an x and one has a y in it. I would try that. If one of them said 2x over x squared plus y squared, the other one said e to the cosine, I'd be like, not a chance. Like they're, you know, when they're not related at all, I can't see how that's going to work. But like this, I'm like, okay, yeah. So I would check to see. I would try to see whether this was conservative, find a potential function, and then use fundamental theorem of line integrals. If that didn't work, if it wasn't conservative, I'd be like, well, sucks to be me. I have to parameterize this and integrate it the long way. So that's what I'm looking for. What questions do you have about number 1? Anything you want to ask? Let's look at number 2. Can I use Green's theorem on number 2?
I don't think so because it's only the right half of the circle and that's not close.
Yeah, so one huge problem is it's just the right half of the circle. It's not closed. Okay, can't use Green's theorem. Maybe fundamental theorem of line integrals? Is that thing conservative? I'm waiting for somebody to catch on to something.
If it's using DS, wouldn't we need to parameterize it?
Yeah, see, if we're using DS, we don't have a vector field. You can't use any of these theorems. These theorems are only for vector fields. Using DS, that means it's a line integral of a real valued function. So there's no theorems, you just parameterize it. You don't have to check orientation for real valued functions. Just parameterize it and you just charge through and do the instructions like it says. So this is a real valued function. I don't need that, I just need this. This is a real valued function. And the DS is also telling you it's a line over a real valued function. You just do it, no theorems involved. Okay. So that's the sort of thing that you'll need to do for each of these problems. And it'll be a good thing for you to have an opportunity to practice that a lot before you get to the exam. So you're a little bit better at it. You get better at everything with practice. You'll get better at this as well. You can see your 20 hours right here, right? Okay.
Unfortunately, yes.
Fortunately, yes. Thank you, Tommy. I know that's not what you said, but okay. All right. Any other questions? Otherwise, I'll send you to the wolves or whatever. Okay, everybody did great last time with the taking the exams. We're going to do it the same way next time. I'll try to get there a little bit early. Well, I will get there early, and I'll check. Have your station set up. I'll check everybody out. Try to have make sure your video is a little bit further away from your paper. There was one person last time. It is easy to do. There was one person last time who had it close enough that I could read what they were writing. So I was like, just back it off a little bit. But everybody did great. We're just gonna do the same old thing. I'm gonna send you the instructions ahead of time, just as a reminder. It'll be just the same as last time, only different content. And I've got office hours on Tuesday. Also, did everybody see? I think I sent an email about how the MLC has office hours for Calc 3. You could do that. I could have a little bit earlier office hours on Tuesday if anybody contacts me, right? I've got the potential office hours you can. So, and other than that, I'll be thinking about you all weekend as I write this exam. You'll be thinking horrible thoughts about me all weekend as you study for this exam. And I'll see you on Tuesday.
Dr. Office?
Yeah.
There's a question in the chat.
Oh, there is. Oh, thanks for, I didn't see that. Thank you so much, sir. As notes from, somebody else called me on that in the earlier class. Somehow I accidentally forgot to upload them. I put the Zoom information in, Zoom recordings in, but I forgot to put the notes in. So I'll do that right now after class. I'm sorry about that. But yes, they will be there. And the solutions and all the other stuff. Okay, cool. Okay, good. I'll see you on Tuesday. Have a good weekend.
Thank you.
Thank you.
Thank you.